All right, welcome everybody to DS3's workshop on anomaly detection. My name is Aidan, and I'm a third-year probability and statistics major.
And my name is Yash, and I'm second-year data science and cognitive science machine learning major. All right, let's get into it. So before we begin, we're going to give a quick preview of the topics that we're going to cover in this workshop. So first of all, we're going to define what anomaly detection is and what are anomalies. And then we're going to go over the impact of anomaly detection and the applications in the real world. Next, we're going to cover how to evaluate machine learning models. And although this is applicable to anomaly detection, this is applicable to the whole of machine learning. Then we're going to go over the categories in anomaly detection and the problems that anomaly detection is used for and the possible algorithms you can use. Finally, we're going to end this workshop with a demo on support vector machines, or SVMs. All right, so what exactly is anomaly detection? So before we begin, let's define the word anomaly. So an anomaly is a non-conforming pattern or observation in data. And this can also be called an outlier, exception, or a peculiarity. So there are three types of anomalies. The first type is the point anomaly, or this can also be called a global outlier. And this is an individual point that is anomalous with respect to the entire data set. And next up, there is a contextual anomaly, or this is also called a conditional anomaly. And this is an individual point that is not a global outlier, which means that it's not anomalous with respect to the entire data set, but it does deviate within a specific context. So context does matter, hence the name contextual anomaly. And this is very common in time series data, where we do see periodic patterns. And finally, there's an anomaly called collective anomaly. And this is when there are a collection of data points that are individually not global outliers, but when combined, they are anomalous. So let me give a couple of examples of these different kinds of anomalies. So with the point anomaly, there's an example with outlier in income. So if you examine the incomes of the US population, the top 0.1% of the earners will have outlier incomes because they'll be extremely high. And since the mean is resistant to, or is not resistant to outliers, these incomes will drive up the mean. And this is why we use the median as the measure of center for incomes. And another example of a point or global anomaly is that when someone who generally does not spend more than $5,000 a month makes a $10,000 purchase. So this raises a red flag, and that would be classified as a point anomaly. Next up, an example of a contextual anomaly would be a sudden power usage surge during the middle of the night. And the reason why this is contextual is because it would not be anomalous, like a global anomaly, for there to be a power usage surge. But in the context of the middle of the night, when people are not using electricity as much, that is anomalous, and that may show that something is wrong. An example of the collective anomaly could be the recent GameStop trading incident in February. So it is not uncommon for investors to buy a GameStop share, but it was a collective anomaly for so many investors to collectively buy the stock and hold, which led the stock price to skyrocket to around $500. All right, so next up, we're going to go over some supervision, what supervision is in anomaly detection. So there are three categories for supervision. There's supervised, semi-supervised, and unsupervised. So in supervised detection, in supervised anomaly detection, the training and test data sets are fully labeled. That means that the normal and outlier points are fully labeled. And you know exactly what point is normal and what point is an outlier. And this makes it pretty ideal, but not realistic, because in the real world, you do not know for sure which points are outliers. So this is a pretty ideal way of anomaly detection. And this is what makes it one of the simpler ways for anomaly detection. And since outliers are very rare, this leads to the data sets being strongly unbalanced because there are so many normal points and such little outliers. Next up, there's semi-supervised anomaly detection. And this is when the training data set is labeled, but it's only labeled with the normal data. So when testing this algorithm and running it on data, we can classify anomalies by seeing how likely they are to be generated under that fitted model. So assuming that the similar to a hypothesis test, you see how likely some point is, assuming that the null hypothesis is true. And it's the same concept in semi-supervised training. In unsupervised anomaly detection, the dataset is completely unlabeled. So there is no distinction between a training dataset and a test dataset. So you do not know what points are anomalies and what points are normal, but your algorithm will be based on the intrinsic properties like distance and density to determine which points are normal and which points are anomalous. And the basic assumption for these 3 points of supervision is that the anomalies are very rare. And next up, we're going to talk about the data inputs and outputs in anomaly detection. So for the input, you can have a simple kind of input or a complex kind. So simple input is when you have tabular data that is independent with one another. And this can be with binary columns, categorical, continuous, or a mixture of all of those categories. And the complex data is when the data are not independent. So this can be with time series or temporal data, or spatial data like graphs or maps or images. And for the output, there are 2 common ways for anomaly detection algorithms to output to have their outputs. So the first way is with binary labels, and binary means 2. So binary would be either 0 or 1. 1 being where you classify the point as an anomaly, and 0 where you classify the point as being normal. And this is more common in supervised algorithms. The second way of the second output type for anomaly detection is with a score or a ranking. And this gives each test instance a score for how normal it may be. And this allows you to rank the results and report the anomalies with the highest ranking, which means that they have the highest probability of being outliers. And this method is more common in semi-supervised and unsupervised unsupervised anomaly detection. And the critical part of using scores is that you do need a threshold parameter. And this would allow you to create binary labels from your scores. So you would create you'd find an optimal threshold where you'd be able to determine that a point is anomalous or not anomalous. All right, next up, we're going to go over the significance of anomaly detection and the applications and what impact it has on our society. So first, on some applications of anomaly detection. So the 3 most common ways are in intrusion detection, fraud detection, and in healthcare informatics. So what exactly is intrusion detection? So intrusion is an attempt to bypass security and gain access to valuable data. And this can often include stealing social security numbers or sensitive bank information. And intrusion detection is extremely important because we're monitoring networks and applications to prevent server exploits and save people's privacy. And fraud detection is detecting criminal activity in financial transactions. And this includes credit card fraud, insider trading, or identity theft. And healthcare informatics is a really broad concept, and there are 2 levels to it. So on a societal level, anomaly detection can be used to detect pathologies and predict any pandemics. And on a personal level, anomaly detection in healthcare can be used to detect life-threatening situations like tumors or abnormal cells. And there are also some more specialized applications of anomaly detection, like image processing and industrial damage detection. So in image processing, one way that it's used is for using video surveillance for suspicious activity. So like in an airport, in that bottom right corner, you could see that there is a bag there. So this is important because that is suspicious activity, and they would use anomaly detection to determine whether they need to intervene or not. And industrial damage detection is detecting anomalies in infrastructure, like power grids, to see if there are any failures or anything that should be anything that's going wrong. And by analyzing these structural damages, you would need to intervene really quickly. And yeah, that's one of the challenges, and we're going to get to that in the next slide. So anomaly detection is an extremely challenging problem, and here are some reasons what makes it so difficult. So first of all, anomaly detection is extremely important, and you need to classify immense amounts of data in near real time, because you may, so if for example, in intrusion detection, you must be able to constantly monitor the networks and detect anomalies before an attack occurs. And this requires you to get a large amount of data and analyze it in a super short time frame and make a decision that's accurate in as quick as you can. And another reason why anomaly detection is so challenging is that there's extremely high misclassification cost. So if you misclassify an anomaly as a normal point, this can be a matter of life or death in healthcare, because on a personal level, this can mean that some person's life-threatening situation could be ignored or possibly just misread. And on a financial level, it can cost businesses tons of money if a threat was misclassified. And next up, normal behavior evolves constantly. And this is evident with network traffic. So network traffic is increasing and the patterns are changing constantly. And if you compare the traffic this year to traffic 10 years ago, or even 5 years ago, it's completely different. And our standard of normality has completely changed. And moreover, anomalies are not binary, and there's a lot of gray area in between. And this requires a lot of domain expertise in the area that you're using anomaly detection, so you can determine what points are more likely to be anomalous and what points are not. And since threats always emerge and they change, your algorithms must be flexible and learn extremely quickly. And since data in the real world is not usually clearly labeled, the algorithm must learn from itself and be able to adapt to new points. And it should be able to address new threats so that you can intervene in time. And finally, a challenge that's often overlooked, but is extremely important, is the ethicality of our algorithms. So in machine learning, there are a lot of applications where ethicality it has not been a concern, but it really needs to be a concern. So when your algorithms are trained on an unrepresented data set, it can yield unjust outcomes. And this is important because these algorithms can change the world, and it's really unfair if they can create unjust outcomes for certain groups. And in that link, there's an example of a fairness-aware outlier detection algorithm that is, there's a paper on that, and I recommend you check that out. And it's because ethicality is a huge concern and should be at the forefront of our minds when we're making an algorithm, and it should be right up there as a priority with the accuracy or precision of our algorithm. Okay, so next up, we're going to go over how to evaluate machine learning models. So we're going to first start off by saying how accuracy is actually a misleading metric. So accuracy itself is the proportion of the predictions that your model correctly predicted. So imagine that you had a data set with, or imagine you reported that your algorithm had 99.9% accuracy. So that means that 99.9% of your predictions were correct. So this may sound great on a surface level, but imagine a data set that had 99.9% normal data and 0.1% anomalous data. So a model that would label every single point as normal would definitely achieve the 99.9% accuracy. But this does not mean that the classifier is desirable, because it was just naively saying that everything was normal. And this is obviously incorrect. And this is a huge thing in anomaly detection because the data sets are unbalanced. You already have a very rare amount of outliers, so you can sort of hack your accuracy up. And this is why accuracy is often misleading. And when anomaly detection is so important and can have such high misclassification costs, it's extremely important that we use the correct metrics to analyze our algorithm. So next up, we're going to talk about confusion matrices. And there's not too much confusing about this, so we'll just go over what exactly it is. So it's really a summary table that describes the performance of a classifier. And it uses true or false, or ones or zeros. And in anomaly detection, the 1 would indicate that it's an anomaly and 0 would indicate that it's normal. So when you have, so in a confusion matrix, it shows what the actual outcome was and what the predicted outcome was. And as seen in the top left square, if you predicted that it was an anomaly and it was actually an anomaly, it's called a true positive. And the true is there because your prediction was correct. And the positive is there because you predicted it to be an anomaly. Likewise, in the top right corner, if you see a false positive, the false would mean that your prediction was incorrect, and the positive would mean that you predicted it to be correct, or you predicted it to be an anomaly. So as we can see, it was predicted to be an anomaly, but it was actually normal. So that would mean that it was a false positive. And this is another name for a false positive is a type 1 error. And likewise, there is a false negative, which means that you classified it to be normal, but it actually turned out to be an anomaly. And this is called a type 2 error. And then similar to true positive, there is a true negative, which means that you correctly identified it as normal. So if you look at accuracy, the metric, if we look at that using the confusion matrix, we can use this formula to determine what the accuracy of the model is. So now we're going to go over some additional metrics that are used, and these are common to anomaly detection, but they're also applicable to general machine learning algorithms. And these are just 4 of them, and there are many, many more. So the first is called recall, or it's also called the true positive rate. And what this means is that it's the ratio of correct positive predictions to total positives. So looking at the formula, it says the TPR equals the total positives over the positives. So the numerator is from our confusion matrix directly, but the denominator can be derived from the confusion matrix. So the denominator says it should be all the positives. So all the positives from the confusion matrix were the true positives, which are the correct ones that you identified as positives, plus the false negatives, because you falsely identified them as negative when they actually turned out to be positive. So that's recall or sensitivity or true positive rate. Next up there is precision, which is also called the positive predicted value. And this is the ratio of the correct positive predictions you made to the total predicted positives that you made. So this one's a little simpler. It's derived straight from the confusion matrix. So it's the total positives over the total positives, or the true positives over the true positives plus the false positives. So it's the correct positives that you predicted over the total positives that you predicted. And next up, there is something called the F1 score or the F measure, which is the harmonic mean of recall and precision. And this, you can also use this formula here to figure out what the F1 score is. And a 1 would mean that it has perfect precision as well as recall. And that would mean that it's an incredibly robust and strong algorithm. And another important metric is the false positive rate. And this is the ratio of the incorrect positive predictions, so false positives, over the total negatives. And the total negatives would be the true negatives plus the false positives. Yeah, and there are a ton of more algorithms or a ton of more metrics for the algorithms out there. And those can be applied in certain situations, but these are the 4 that are more applicable to anomaly detection. And now we're going to go over what the ROC curve is. So ROC stands for receiver operating characteristic curve. And this is essentially a trade-off between the true positive rate and the false positive rate. And what it does is it displays these 2 metrics for various thresholds for a single classifier. So as you remember, a threshold is the value for scoring a specific datum into a class label. So it's the level at which you would consider the level at which you would consider a datum an anomaly or a normal point. So the goal for the ROC curve is to find an optimal threshold for classification. And although the default is 0.5 for a balanced data set, you usually do not have a balanced data set because anomalies are very rare. So you would use an ROC curve to determine the optimal threshold for the unbalanced data sets. And as you can see on this graph here, the diagonal shows a completely random model. So it has the same true positive rate and false positive rate. So you would want a more optimal model, and any model that goes towards the top left would be optimal because you want something that has a higher sensitivity or a true positive rate and a lower false positive rate. And next up, to compare specific classifiers, you can use the area under the curve, or it's called the AUC. And this provides an aggregate measure of the performance of a classifier across all the possible thresholds. And this ranges from 0 to 1, and a higher proportion would be indicating that there are better predictions for that classifier. And this is really useful because it has no units, and this allows you to compare multiple classifiers. And next up, Aidan's going to talk about the specific algorithms within anomaly detection.
Okay, so yeah, as Yash said, I'm going to now talk about some anomaly detection algorithms. So here we have it's not full everything that you could possibly do for anomaly detection, but we just kind of enumerate for point anomaly detection. So earlier on we had said that there's contextual ADs, collective ADs, and point ADs, and there's also some other types that are more specific called distributed anomaly detection and online anomaly detection, but we omitted it from this, and we can maybe talk about that in a later workshop. But so for point AD specifically, which is a bit more simple, as we talked about, collective and contextual get into more complicated data schemes, maybe with time series data and the like. So we have clustering-based algorithms, right? So that's going to be using different clustering-based algorithms, and then we have nearest neighbor-based, right, where we're considering distance, and then we're also considering density. So distance would be, we're measuring the distance from points, and trying to model that in the best way possible. Density would be kind of similar to clustering. So the distinguish here is not crazy, but anyways, then we also have classification-based algorithms where we're using maybe neural networks. There's some popular stuff going on now trying to use neural networks for anomaly detection, using rules, which would be using what Yash talked about earlier with the true positive rate and false positive rate, and just trying to use probability theory and that sort of stuff in that sense for classification. And also support vector machines can be used in a classification-based sense, which we'll talk about later and go over in our demo. We also have some statistical methods that are a bit, those are a bit more old in the sense that, we have newer methods, probably focusing more on classification-based methods and nearest neighbor-based methods, but parametric and non-parametric are still there. And then some others I listed, so information theory-based, spectral decomposition-based, and visualization-based. But we're mainly going to focus on classification-based for this workshop. So yeah, so as I said, so we're going to be in point anomaly detection, and then we're in classification-based. So for classification-based techniques, right? So not just for anomaly detection, but on a broad scale, our goal is to train a model using whatever available labeled data and use that model to classify unseen events. So here, right, the data, as we mentioned earlier, has kind of an indication of what we will expect from the model. So if we have fully labeled data, so it's, we're in a supervised sense, and it's the best case possible, we know the anomalies and we know the normal values of the data or whatever the cases are, then we want the model to be able to distinguish between the two. So if we give it a normal, right, we can kind of draw a line and we know what are anomalies and what are normal values. Now, the semi-supervised sense would be we have a data set where we only know what's normal, and we want to essentially learn what is normal in this data set, kind of have teach the classifier to know what is normal, and then as we give it new data, have the classifier be able to tell whether this is an anomalous value or if it's just normal. And that's essentially what we're going to be covering in our demo. So one important note here, right? So as Yash had mentioned earlier, classification models need to handle the skewed distribution because, we have a data set with both anomalies and normal values. Anomalies are rare and they're not going to be as many values. So we're going to, need to make sure that our classification model doesn't overfit and just kind of, really learn the normal distribution, but not learn anything about the anomaly distribution. But anyways, that's more so for the supervised sense, which is a bit unrealistic in practice. So some pros and cons, as I mentioned, about classification. So for both, the unsupervised and the supervised case is we're creating models that are fairly understood, right? So it's kind of like the converse of a black box, call that white box. It's essentially, we know what's going on. We know what we're trying to predict. We're essentially doing binary classification type methods. And we kind of, know our goal. So nothing crazy going on. And then for supervised, a particular pro would be that we expect there to be high accuracy in detecting the different types of known anomalies. So because we've given the model, labeled anomalous data and normal data, it should have a pretty good sense and a pretty high accuracy of knowing the anomalies. We mentioned earlier that accuracy is not a great metric, but if we do know there's a certain amount of anomalies, we can test essentially our accuracy on anomalous data rather than accuracy on everything in the data set. But some cons, however, are, of course, as we said before, it's very unrealistic to have labels for both normal and anomaly data. Those classes, maybe we just have a data set and maybe we only know what's normal. Maybe we don't know what will be anomalous in the future. That's always a challenge. And that's what I'm getting at here with we can't detect unknown and emerging anomalies. So something that's normal today might be anomalous tomorrow or in 10 years. And same goes for anomalies. Things that are anomalous today could be normal in the future. I mean, for example, internet traffic years ago was much lower than it is today. And if all of a sudden the internet had, the amount of, users that it did that does today, 10 years ago, that would be a huge spike in the data. So you just kind of have to weigh out these things. And then for semi-supervised, we require normals, and because we only know what's normal, we have a high chance of just saying that anything that we haven't seen before is anomalous. So that's what we talked about with our false positives. So our false positive, to give you a reminder, is when we are saying that it is, for example, anomaly, or it is true, but it's actually not true, right? So we're saying it's we're making one prediction, but we're actually incorrect. So we're classifying it as an anomaly, but it's actually just normal, and we just haven't seen it before. Maybe it's just a little bit out of the distribution, and we just haven't learned it good enough. Anyways, so support vector machines, as I mentioned earlier, they kind of fell in the classification-based area, but they can also be, interpreted and learned in a more of a density-based problem. So the literature is a bit, it's all kind of connected in a sense. So I kind of, explain a bit of two ideas you could approach here. So as I said, we can use support vector machines, which we'll kind of, give some intuition behind in our demo, but we could use them for a binary classification type problem. So this was proposed by Steinwart, and I think it was roughly 2005 time. So essentially what we're saying here is, we have a data set, it's labeled, it has normal data and it has anomalous data. And what we're doing here is, we're assuming that normal events will be in these high density regions, and anomalies will be in these low density data regions. So we can use some sort of unsupervised approach to learn these different densities, and then essentially use a modified version of the standard support vector machine to classify the data density level. I won't go into too much detail about that, because as I said, it does get a bit confusing, but essentially the intuition behind it is that we're taking the traditional method of support vector machines and we're kind of modifying it to convert to a binary classification type problem. But what was a bit earlier on proposed, and this is what we'll be covering in our demo that is implemented in scikit-learn, is essentially converting the problem to a one-class classification problem. So we assume we only have normal data, and we're going to essentially separate the regions that have all the data, and that's our normal data. And anything new, right, should be able to our classifier should be able to choose, okay, that is an anomaly or that's not an anomaly, right? So it's kind of just like a, if it's normal and we've seen it before, we'll say it's normal, and if it's not, it's not. So this is going to lead us into our support vector machines demo. So, oh, slide too far. So we're going to go into here. So that notebook is available. I linked in the slides, but the if support vector machines weren't clear, and like as I said, those distinctions between the classification and the density-based methods kind of get a little, I don't know, the lines are a bit blurred. So this hopefully will help clear things up a little bit. So this is originally a tutorial on scikit-learn's website, so you can view that here. But I modified it a little bit to make it a little bit more interpretable. So anywho, let's kind of get started with this. So initially, we just have our basic data science libraries, setting up our environment, getting everything started. And I actually don't end up using this local outlier factor. But so we're using NumPy, matplotlib, and from scikit-learn, we're going to be importing the SVM library, and then Seaborn for some plots. So first, as I said, we didn't really discuss what are support vector machines. I mean, maybe you've heard about this, maybe you haven't. Oh, let's make sure we can run this notebook. Okay, great. Yeah, so as I said, we didn't really talk about what support vector machines are, why we use them, what's the idea behind them. So this is something that can be discussed for, 1 lecture, 2 lectures in any type of, machine learning class. For example, in like CC 151A, you might cover this, but I'm just gonna give a quick intuition, and maybe we'll go over this in greater detail in further workshops. It just requires a bit more math, and that's not really the point of what I'm going for today. So our goal, right, essentially is just to find a line or a curve. So as we go up in dimensions, that changes. So essentially we just define this as a hyperplane, which is essentially just, a hyperplane is a line and a curve and a manifold that kind of just encompasses everything. So, we have this simple data set, for example, and we can see that there's 2 classes, right? So the red dots are some sort of class, and the yellow dots are some sort of class, right? So what we want to do here is essentially, separate the data, right? And we need to draw a line for that. So if you thought about drawing a line to separate this data by hand, there's a lot of different lines you could draw. So we could draw one, we draw one here, and that's kind of what I'm expressing here. So, right, so say we're to just draw 3 lines, these are just arbitrary 3 lines done in code. But, that line just separates the data, right? This line separates the data, but which one is the best one? How do we know what to pick, right? That's kind of the problem, and that's kind of where support vector machines, help improve on this, right? So as I write here, the intuition is, instead of drawing this line with just 0 width, right? So we have no width, which means say this doesn't touch it, that's fine, right? It's not touching red dot, not touching yellow dot. It's completely separating them. Same with this line, it's completely separating things. But if we draw a little bit of width on it, right? So we classify this as a margin, this gray area here. So we draw a little margin around our lines. So yeah, and the size of the margin is kind of up to some point. You might decide that a certain value is better than another, but anywho, so now we see, okay, well now this margin, I mean, obviously, intuitively, that this line here is probably not the best line, but now we can see, okay, it's clearly, it's hitting some yellow dots, and this line is getting really close to some red dots. So what support vector machines do is it's going to find the line, or the hyperplane essentially, and if we want to be broad in a sense. So the hyperplane that maximizes the margin, right, is the one we'll choose. So this kind of represents this as a maximum margin estimator, and that's just kind of like a an overview. And as I say here, just if you were to skip all this, the main point, the main takeaway of this is that we're separating 2 classes if we had a 2-class setting with a hyperplane that has the largest possible margin. So as I said, very brief, quick little intro, motivation, some intuition. So if you want to read more about support vector machines, you can check out the Wikipedia page. It's got a lot of information on there about support vector machines and kind of all the different parts of them and all the different types. There's a lot of different types and implementations. And what's interesting is support vector machines can also separate data that's not linear. So here we have a problem that's linearly separable, right? We can draw a line and it's able to separate the data, right? But what if we couldn't draw a line that separated the data? So the idea is we can start going up into higher dimensions, and our data no longer becomes a line. It starts becoming curves and manifolds and that sort of thing. And that's where it gets kind of mathy and a bit harder to understand. So as I said, I'm gonna kind of just brush that under the rug for now, and you can check that out. And then for some information on using support vector machines for anomaly detection, like that case particularly, this is a great paper that kind of goes over it, but again, very mathy and very detailed. But anyways, so have we ran everything? Okay, cool. So yeah, so now that's kind of the idea, but what what we want to do here is go over scikit-learn's one class SVM model. So you can use this model for the problem of novelty detection, which on the website, they have some information on outlier detection and anomaly detection, and they kind of separate the two into a sense of like outlier detection being almost an unsupervised problem, and novelty detection as like a semi-supervised problem. So the distinction is not that important here. You can go read about it on the documentation, which I believe is linked through here. So anywho, one class support vector machine is essentially the second thing that we mentioned here. So that was let's go back and do it real quick. So that was essentially this, right? So what was proposed on the second one, right? So we have a data set that only contains normal data, and we're breaking this into a one classification problem. So what the actual library that the support vector machine is modeled after is from that paper. So, right, so our idea behind this is we want to find a function that is positive for regions that have high density of points, and it's negative for small densities. So we're kind of, figuring out a way to separate the data. Essentially, instead of using a line, we're almost using like a sphere that's kind of, fitting our data properly and kind of, like learning a boundary essentially. So this is what I find to be the best explanation of the problem, which is from scikit-learn's literature, or like article, I guess, tutorial on anomaly detection. So we want to consider a data set of observations from the same distribution, and it's described by some features. So consider now that we add one more observation data set, right? So we take, we've got some data, and we added a new observation, right? So is the new observation so different from the others that we can doubt it as regular, right? So does it come from the same distribution? Like, is it an anomaly? Like, how can we understand how this new data point relates to everything as a whole? So that's essentially the problem that this is facing, and a bit more of a wordy and like math related intuition is just talking about right. So the idea is that the algorithm, which the algorithm is the one class SVM. So it starts with a number of training points that are supposed to fall into the region, and then it estimates the region with a desired property. So as the author mentions, there's often many different regions. So I didn't talk about this earlier when I talked about support vector machines, but there's this idea called kernels, and I link some resources later on. But a kernel essentially is a certain way that we can transform the data and solve nonlinear problems. So there's linear kernels, and then there's nonlinear kernels. So what we're going to do in our demo is go over one class support vector machine using a nonlinear kernel. So anywho, that's all the background information kind of we need, and this will go fairly simple now. So first, we're not using a data set that's anything special. We're just going to generate data and just kind of random data, generate some anomalies, and go from there. So just quick notes on the randomization of the numbers, just to understand. So rand-n is going to sample from the normal distribution. So mean 0, standard deviation 1, or sorry, variance 1. So that's what we're doing here. We're generating some random samples, and from the same distribution, right? So from the same normal distribution, we're going to use rand-n for the training data and rand-n for the test data. So these are our novel observations, right? These are our normal observations. These should be detected as normal. And then to generate some outliers, right? We're going to essentially take a uniform distribution from -4 to 4, right? So that means we're going to just say, imagine a number line that's continuous, and -4 is the bottom and 4 exclusive is the top, and we're just going to grab numbers randomly from there. So and we're going to grab 20 of them. So we run this, every time we run it, you're going to get different observations. So if you were to continuously run this notebook and you wanted to reproduce, you could explore setting the seed, but that's not really the point of this workshop. So here, I just kind of wanted to give some intuition on what this actually, becomes. So xtrain is a big matrix, right? So essentially we have XY coordinates. So here's our matrix, right? So we have 200 samples, and this is, just decimals, just float values that are, randomly generated. And then X test, looks kind of just like that. We don't really need to print it out. It's the same sort of thing, but notice again, so we picked X outliers, and it's going to be 20. There's going to be 20 outliers, 200 X's, and then 40, test values. So just, quick, note, if we look at here, so right, we see a lot of 2s, we see a lot of 1s. This is looking like pretty, constricted to one area, if we were to, imagine that. Here we have, we have some 0 values, we have some negative values, negative 3.6, right? So like, this is clearly an outlier, right? And this is just viewing the first 5 samples. So anyways, that's what our data is looking like. And so now we can kind of move into model fitting. So for this particular support vector model, what we need to do is we need to choose a kernel. So as I said, I kind of brushed that under the rug. You can read about it more in the support vector machine implementation. They've got some interesting information on kernels. Anywho, so we need to define a kernel, and RBF is a nonlinear kernel. It involves a parameter gamma and the exponential function, but I believe the exponential function. But anyway, so we're gonna define this kernel. RBF is like a traditional one used, and for each problem, one kernel might work better than the other. So I'll show this for RBF first, and then for as an example of what would be a bad choice, I'll show the linear kernel after, and we'll show that our model gets really different results. So yeah, so we're going to define a kernel, right? And that's what we're defining here. Kernel equals RBF. So that's just defining the default kernel to be the RBF kernel. A scalar parameter gamma. So we're going to set gamma to 0.1, and that's going to define our frontier, right? So what we're going to be learning is this frontier. So our kernel function essentially defines this frontier. And then we have a new parameter, which essentially is called, the margin of the one class SVM that we kind of discussed earlier up above. So it's the probability of finding a new but regular observation outside of the frontier, right? So we want to know, how far can we go outside of the of our region and maybe still get normal values, right? So this new parameter can be, different for different contexts. So here, from the scikit-learn tutorial I had mentioned earlier, they use 0.1. That's what works best for this problem, but you could have a problem in different contexts. Maybe it needs 0.2, and our model will be better. So often it would be good to, fine tune this this model with, testing different values for the hyperparameter. So anyways, that's kind of, an intuition of what's going on with our support vector machine classifier. And then just a quick, if you haven't ever seen scikit-learn or any, R packages, fit is just going to detect, it's going to fit the model, detects the soft boundary of the set of samples X, and predict X is going to perform our classification. So for the one class model particularly, we're going to get, binary values. So we're going to get +1 and we're going to get -1. If you were to use one of the other scikit-learn classifiers for support vector machines, these might be more on a range of 1 to -1 or something like that. So as I said, kernel functions aren't explained here. And if you're interested, I'll just show you guys this really quick. So scikit-learn's got a great little bit of information. So this is a kernel we're using, the RBF, which, as I said, very mathy. This is our gamma parameter, and no need to go over that. But if you're curious, you can check that out. So run the cell, and we essentially fit the model. We have a very small sample, so essentially our data gets fit immediately. And then we'll print out some accuracies. So as we talked about before, accuracy is not a great metric. We could also use confusion matrices and F1 score and precision recall. I didn't implement that here, but you could also extend that and add that there. But so it looks like for our classifier, so in terms of the training set, it's getting about 90% correct, 82% correct on the test, and it seems to get everything right for outliers, which means that I guess maybe I should note here. So when we make our predictions, we're expecting that predicting for it's a Y predict train, that should be all positive values, right? So all positive values here being, being +1 or -1. So we should be getting all, all ones. And if it's a -1, right? So if Y pred train equals -1, then we're like, that's an incorrect prediction, right? So same goes for test, Y pred test, -1. And then here, if the outlier value is predicted to be 1, right, that's a misclassification because those should be considered to be -1. Anyway, so that's kind of an intuition about what's going on there. So we run that, and now we can start visualizing our results. So decision function is essentially going to compute the sign distance to the separating hyperplane. Again, kind of brushing all that stuff under the rug in terms of, why that works and how it works, and, the proofs and stuff behind it. But anyways, what we're going to get in the end is this. So essentially, these contour lines here, so like these different blue lines, are the learned decision function. And this is learned decision function, particularly for the RBF kernel. So that just kind of wanted to make sure you guys saw that first. But so going through our code, right? So essentially, we're just going to prepare our decision function here. Lots of different little matplotlib and just NumPy like syntax things that are going on. Don't look too far into it. You can check out the documentation and other tutorials for similar things like this. But anyway, so we prepare our decision function, and then we just build up our plots, right? So here we're plotting our our decision function boundary, and then A. So A is our learned frontier, right? So this red circle here, these red circles are essentially what we're learning the normal data to be. So this is our this is our line, right? This is what, we couldn't just separate this with one line, right? Because the outliers are all around, right? So there's not really a line that just goes through and cuts this right in half and solves it. So this is our learned function, right? And that again is dependent on the kernel function. So anyways, then we go along and we plot, the different dots and that sort of thing. But so again, we noticed that we got 20 out of 200 for our errors. So, we're not getting everything, but, we seem to have gotten that. So what I want to just really quickly show to end the tutorial is if we change, sorry, let me find it. Okay, so say we change, first we'll just change the new parameter, right? So we had 0.1, let's change it to 0.3, right? So say we just didn't know what we were doing and we just picked a random value, right? So now our accuracy is getting a lot different. So 70.5, 57.5, but we still somehow get accuracy on the outliers. Again, this is random and, we don't have a lot of data, so not too crazy. But now, we're doing okay, but still not great. But anyways, so that's just an example. Like now let's maybe try 0.2. So sorry, where'd that go? So if we decided that our margin is going to be 0.2, we did a little bit better than we did with 0.3. Again, and so, that kind of thing. But so what will really change our results is changing the kernel to, say, for example, a linear kernel. So if we change to a linear kernel, this is going to have an entirely different picture and entirely different accuracies, right? So now we notice like, wow, like we really just totally decreased what's going on. So everything just is really performing badly. And we can see that now with our results. So as I said, that the contour curves we were learning are much different. And this is not a linearly separable problem, right? So what we discussed up here, talking about drawing a line to split everything, we can't do that here. This isn't like, a problem that could just be, one line that separates everything. So, if we were to do that, right, we had no idea what's going on and we just throw a random kernel function in, this is what happens. So that's kind of the end of what I wanted to talk about here. But anyways, you can experiment with different functions and check out the linked kernel functions here, right? So I mentioned that. So that's just using a linear kernel, but what we used here was a RBF kernel. So anyways, that's that wraps up the workshop. I believe there's some other links in here, as I said, so there's other links here, be sure to check those out if you're curious, what's going on here. I know I kind of treated this as a bit of a black box because we only have a short time, and you can cover support vector machines in a whole class. So anyways, thanks for watching, guys. And I hope you guys were able to learn something.
Yeah, thank you so much. And on the last slide of our workshop, you're going to see some resources that we used and we found incredibly helpful when we were creating this workshop. So yeah, so feel free to check out those links. They're extremely helpful. And yeah, that's how we learn. And we hope that if you have any questions, feel free to reach out to any one of us. And we hope you learned something from this workshop. Thank you so much for your time.
Thank you. Bye-bye.